Hi, my name is Doug DeYoung and I'm one of the co-founders of Bug Amps. And this video is going to be a deep dive on the phenomenon of blocking and crossover distortion caused by blocking in class AB1 push-pull, obviously, capacitively coupled, fixed biased output stages. And so that's a mouthful, obviously, and it may sound like an edge case, but that's actually most amplifiers, or most push-pull amplifiers, fall into this category. And so this is why it's a big problem, and this is why I'm making the video. So here at Bug Amps, we've developed a circuit called Bug Bias, and it is a solution for blocking distortion, and it's kind of a novel solution that I haven't seen before. And so I hope you enjoy the video and get something out of it. I should tell you that the circuit itself is going to be available in a link under the video, so you can download it and have a look at it and see what you think. This is my sort of formulation of this idea, but obviously I've used a transistor. You could also use a FET or a triode, or even just a single voltage divider and a diode there and accomplish the same thing. The voltage divider diode solution would only work if your negative voltage source impedance is sufficiently low, so that's why I haven't done it that way. And so I should tell you that the other co-founder, my partner in crime, Sean O'Neill, is going to be creating an in-depth measurement article on bugamps.com looking at what exactly the circuit does to amplifiers. So when he gets that done, we'll all be looking forward to that. And also at the end of the video, I'm going to show bug bias in action on my scope, and also a screenshot of the Spice sim that Sean did. So I hope you enjoy the video, and I hope you get something out of it. All right, this is going to be a video talking about how to fix blocking distortion in class AB1 capacitively coupled tube amp output stages. And first, I'm going to talk a little bit about what blocking is and what kind of distortion it causes. And we're primarily going to be talking about electron flow as opposed to conventional current flow here. So we're going to be thinking about electrons and what they're doing in the circuit. And so here you can see, now obviously I'm saying this is AB1. I'm showing one side here. There's a pair of these output tubes, and they're going to be sharing the signal for some of the time, and then for some of the time they'll be handling it. You know, each one will be handling one side of the wave by itself. So what happens is you've got signal coming in here. The AC passes the capacitor and comes over here. Over here, the signal is superimposed onto a negative bias right here. And the negative bias is here to make the grid negative to prevent electrons from flowing from ground, which is 0 volts, through the cathode to the plate, which is some positive voltage. Positive voltage meaning a lack of electrons. And the way it does this is it's charged negative by this negative bias voltage, and the electrons sort of pack up right here, and electrons repel electrons, just like a lack of electrons attracts electrons. And so you turn the tube off by making the control grid negative compared to the cathode. So if you make the control grid negative enough, you turn the tube off. And if you don't make it negative at all, you turn the tube all the way on. And what you want with an AB1 amplifier is you want some of it to be in class A, and so you want the tube to be on, but not on all the way. And so you have something called a bias current that's going this way. And so some of these electrons are going past the grid to the plate, and the amount of electrons is called amps, or current, in this case milliamps, and so it might be something like 20 milliamps or something. And then goes through our output transformer and to our positive voltage source here. So you can see that the negative bias is important and that it controls the bias of the output tubes. And if it were too low, if it were very negative, then we would have an issue where the tube would be off. And if it were quite positive, the tube would be on all the way and it could melt basically, because you run a bunch of current through it and it has to dissipate a lot of power, etc., etc. So what happens with blocking is there are some situations where electrons can flow from the cathode here this way. And why that happens is there's something like a diode action here between the cathode and the grid. And the reason why this is if this area over here becomes, let's say, 0 volts, or even positive, like if this cap fails here and some of the positive voltage from your plate of your previous stage gets over here, this could even become positive over here. And when that happens, there are no longer electrons here to prevent flow from the cathode to the plate, but those electrons will flow anywhere that's more positive than the cathode. And so if the grid becomes more positive than the cathode, they will readily flow into this circuit, thereby making it more negative than it is. And so that can happen if this fails, or if this voltage here is incorrect, or if the input signal swings more positive than 0 volts, which is ground. Okay, so we're going to simplify this to make it easier to look at, so I will switch to that now. Okay, so this is our simplified diagram here to show what happens with blocking. And so in a proper functioning circuit, which is what we're going to be looking at here, where the capacitor is not leaking and our negative voltage is correct, you can see that the negative voltage flows through this large value resistor. This is so that the negative voltage supply doesn't load down the high impedance signal from the plate of our previous stage. I've replaced the tube and all that over here with a single diode just to show that the impedance here is very high until the voltage here rises above 0, at which point the diode is turned on. So this is the grid cathode diode action over here. And once it reaches 0 volts, then the diode turns on. But during normal operation, when the amp is not clipping, that never happens. And so you'll have signal here, and a signal will swing up and down, and it's going to swing up less than 20 volts, not reaching 0 volts. So let's say this is 0 right here. So it never reaches 0 volts. The diode is never turned on, and so there are no problems. The average negative voltage stays the same, because you can see that the area here is the same as the area here. And so the average here of negative 20 doesn't change. So that is the proper functioning of a capacitively coupled AB1. This is a single output tube device. Obviously there's 2 of them that are handling the signal here, but we're only looking at 1 for now. And this is functioning correctly. Alright, here's our next diagram, and you can see now that we have an input signal, a signal from our driver stage, that's now swinging more than 20 volts on either side here. And so the tops are more positive than 0, and suddenly the driver stage previously was swinging against a turned off diode, so that's basically infinity impedance over here. and it was also swinging across 250K, which is a large load. Typically, the plate impedance of a driver stage might be 30 kilo ohms or something like that, and so it's happy enough driving 250K load. But what happens is when the signal from the driver stage approaches zero, and then reaches zero, this diode turns on. And so suddenly, like a switch being turned on, now the diode between a grid and a cathode is not a perfect diode. It's a very imperfect diode, but it's enough like a diode that the load that the previous stage was experiencing now drops to whatever this is when it's turned on, which is not very much, a few thousand ohms or something like that, and whatever the value of your grid stopper is. This is the grid stopper. And so you can see that suddenly the impedance drops, and when the impedance drops, it clips the waveform. And another way of thinking about this is that when this diode turns on, electrons start flowing like this. They come through into this network here, and they start accumulating in this area here, and their only way out is to go this way. But you can see there's a large resistance value here, and so there is a time constant between the cap that gets charged up by this and the value of this resistor and whatever the impedance of the negative voltage supply is. And so this is called blocking. I think it's so called because the coupling cap blocks the electron flow from the cathode to the grid in here. And so when electrons accumulate, things become more negative. And so every time this waveform clips, electrons jump in and make this more negative. And so this stays negative 20 here, but if you dramatically clip one side of this wave right here, this will start to drop. And so if you actually take an output stage that's suffering from this, which is most AB1 capacitively coupled fixed bias output stages suffer from this, and you put your meter here and you clip your amp, I've seen these drop 15 volts very quickly. So you might get negative 35 or more volts here. And that is, like previously mentioned, this voltage here is what's controlling the bias current of the tube. And so if you make this much more voltage, the bias current of the tube drops, so it goes down, and could even turn off, and in many cases does turn off. And so in an AB, at that point it's now a class B amplifier, a B1 amplifier, if the output tube turns off. And we'll talk about why that's bad in a minute. But another way to think about this is an area. So you can see that we've got an area here, just like in the previous one, and that area is less than here. And so asymmetric clipping, you can see that it's becoming more negative each time it goes through. Also, you'll notice that when you clip off one side of waveform, you've sort of created a not very good half-wave rectifier. And as rectifiers do, they create DC, and so this is half-wave rectifying a little bit, negatively rectifying into negative DC, and that negative DC adds to the average negative voltage of this network. So that's three different ways of saying the same thing. Three different ways of looking at it the same way. So this is what's happening, and what does that do? I will show you. So quickly, this is the input wave right here. If the output tubes are off, the middle of the signal right here in the middle does not get amplified, so it just removes it. And what happens when you remove it, you end up with something that looks like this, like that. And this is called, as you're probably aware, this is called crossover distortion. One of the causes of crossover distortion is blocking, which is what we're looking at today. There are other causes of crossover distortion, just like incorrect bias is the other main cause of crossover distortion. But today we're looking at blocking. So this is what it's going to look like on your waveform. It's actually not going to look like this exactly, because in an AB1 output stage, when you reach 0 volts, you're already at visible clipping. And so the output waveform with the blocking caused crossover distortion was actually going to look like this. Because once you reach 0 volts on an AB1 capacitively coupled output stage, you're going to clip here, obviously, and you're also going to have the crossover distortion. So this is what you're going to look like. This is undesirable. You don't want that. You're always going to have clipping with an AB1 capacitively coupled output stage when you reach 0 volts. But this kind of clipping is preferable to this and this. These show up in your harmonic spectrum as 4th through like 7th order distortion, harmonic distortion. Harmonic distortion, I guess you don't need that there. These guys right here are a much more musically acceptable third harmonic right there. And so also just knowing that when you see this, you know, oh, my output tubes are off. There's a whole portion of my signal that's not even being amplified. It's not good. You don't want it. And your tubes can turn off more and more the more signal that is applied. So it's no bueno. Anyway, this is what you're going to see on your scope. And you don't want that. Okay, so back to this. So there are lots of ways of fixing crossover distortion or mitigating it. Most of the ways are, well, let's just look at a few of the ways. So one popular way of fixing this whole thing is to change the class of the amplifier to AB2. Excuse my handwriting. AB2 means that your driver stage, this guy right here, is sufficiently low impedance so that when this diode turns on, it continues to have the current available to just bring that waveform back up into positive territory. And that's just great. If you can do this, you know, knock yourself out. But you can't really do it with a capacitively coupled plate-driven stage. You're going to need to add something called a follower stage, and that usually is a MOSFET or a high voltage transistor or a cathode follower tube stage. So you're talking about an entirely new stage over here. You're talking about, you know, adding more complexity to the circuit, which is fine. You're going to get more power out of it too, because as you drive 0 volts, the grid actually starts acting kind of like a screen and accelerates the electrons towards the plate even more. And well, that's great. You can do that. Another way of doing it is to couple with a transformer. And transformers obviously pass DC. And so they don't block. So there's no blocking distortion. However, just because you're transformer coupled doesn't mean that you're low impedance enough to drive to positive voltage. So it may still be AB1, even if you're transformer coupled. And what that means is there's no charging of this cap, but you still may have clipping. And as we looked at before, if you're clipping, at least momentarily, you're creating a little bit of a negative half-wave rectifier situation that will briefly lower the bias of your output tube, but the recovery will be very quick, and that's the main thing, so that's also a good option. Another thing that people do is they take the value of this grid stopper and they make it very large, so they may make it 50K or something like that, and that's fine. It comes with some problems, but it's good because now you see when this diode turns on, the waveform over here is still going to be clipped right here. But the waveform over here, you know, this 30K plate plate impedance may be perfectly happy for a brief period of time driving this 50K load right here. But still, you're running into the same problem. Over here, your waveform is going to look just fine running into positive voltage, but over here on the grid, it's still going to be, you know, doing this like that. And once again, you're back in a negative rectifier clipping situation. Also, having a very large value here it just adds in series to the impedance of the plate here, and you have something called Miller capacitance between the grid and the plate, and the higher this value is here, the more high range you may potentially lose here, which is not a big deal in most cases, but in some cases it is. Also, having very large resistance values on the grids of tubes is usually bad for noise performance. And so you're going to have increased noise doing that. So this is a good solution, but it's sort of mitigates the problem as opposed to fixing it. It does somewhat keep it from charging over here, though. Another thing that some people do is they will take the value of this capacitor and they will make it smaller, and they do that in the hopes of decreasing the time constant between this value and this value so that the amp recovers from blocking more quickly. Or you could take this value and make it smaller, and what that does is it allows the electrons to discharge more quickly, thereby decreasing the time constant of the circuit again, making it recover more quickly. But the problem with all of these, except for the follower stage one, is that they just cause the amplifier to recover from blocking more quickly. Over here, as long as we're still in AB1, we're still having a temporary situation where we're half-wave rectifying to a more negative voltage than we want right here. So what is the solution for this? I will show you. Okay, so here we have an actual non-mitigating solution for blocking distortion in capacitively coupled AB1 fixed bias output stages. And I'll draw it in right here. It looks like this. Now you've probably seen this before. I found it on the internet. I did not invent this. You have a Zener here, and the Zener is set for twice the voltage of the negative bias, so in this case it would be 40 volts. And what this does is it just clips the negative waveform at twice the bias voltage. So we got negative 20 here, down here at negative 40, we're clipping the ground, and up here at 0, we're also clipping the ground. Got it. So this fixes everything, basically. When we go positive of 0, electrons come in, like that. And if we have these values correct, when we go negative, the same amount, the same number of electrons go out. And so you can also see over here that the areas are now the same, and so we're not half-wave rectifying to a more negative voltage anymore. We're always clipping symmetrically here, and the average voltage here will always stay at negative 20, regardless of the signal coming in from our previous stage. And so that works. I've tested this on the breadboard and it works fantastically, except for you're probably seeing the problem. The major problem is that if you want a different negative bias, you have to change the value of the Zener, which is not practical, because obviously as tubes age, different tubes need different negative bias. As tubes age, they require less negative bias for the same current. You may want to change the bias of your amplifier at some point, and you can't just be going in and replacing Zeners till you find the right one for your bias point. That's a mess. And so, but as you can see, this does actually fix the problem. Another thing I should mention is you might think, oh, isn't it going to cause more distortion adding extra clipping to the signal waveform? And the answer for that is no. One, the output waveform is already clipping. You've reached 0 volts in your AB1 output stage, and so you're visibly clipping on the wave scope already. Also, it's good to remember that this, basically below a certain point here, your tube is off. So this is cut off right here. This is the cutoff region already. And so clipping the waveform down here doesn't really affect distortion. The only thing it does is normalizes the negative bias voltage and eliminate blocking in this area right here. So that's great. That's what we want. But how do we do this in a way that it doesn't require swapping out Zeners every time we want to change the bias? Well, this is where what I feel like is sort of new and novel about this whole video. If you watched this far, good job. But now we're getting to the bit that I think is new. I've scoured the internet to see if somebody else has thought of this. I haven't found anything else that's like this. I did find a cathode biased version of this called a DC restorer circuit that was created by Bob Carver, but his was for a cathode bias, and it was quite different than what I'm about to show you. So I think I've invented this. If you can show me that I haven't invented this, please leave a comment or whatever. But I think I've invented this. I'm calling it bug bias because bug amps, of course. So here we go. All right, here it is. Bug bias. Excuse my poor handwriting. All right, so this is my circuit, and you can see we've got a transistor here, got a couple of Zeners, got some resistors, diode, and if you're looking at this and you're thinking, I don't want to put that in my tube amp, have no fear. This whole circuit is completely off until you clip your amp, and in that moment when you clip your amp, it turns on, and it acts just like that Zener in the previous example. So I'll show you how it works. Over here, we have to supply the circuit with 2x our desired negative voltage. Negative voltage, that should be negative, obviously. And so over here, we get our desired negative voltage out. And these guys right here are a voltage divider, and so they will be the same value. These values can be quite high. 150K or something like that is probably fine in most cases. Something like that. And so you can see immediately voltage comes in, gets split in half, and half the voltage comes out over here. So let's just, for fun, we'll just say 20 volts is what we want again. So we'll just do 20 volts, negative over here. And over here we'll put in negative 40 volts. And so right through here we're going to go down to negative 20 right here. This resistor right here, this is our grid leak position, and so in the previous example we were using a 250K, so we'll do that. This should be chosen depending on the tube that you're using in the data sheet and the driver stages, what it wants to handle and all that. And so, but you can see that negative 40 is going to come up, so this resistor here limits the emitter base current, and so it can be something like 30K or something like that. These are all adjustable to make the circuit work in your particular situation. This Zener right here can be a couple of volts, like 2 or 3 volts. Let's say it's 3 volts, and this one can be you know, 2 volts or something like that. This Zener right here just prevents the base emitter voltage max from being exceeded, and this one right here is just to prevent the current that this is going to draw from being pulled unnecessarily from the negative supply over here. And the values are not that important. They'll work regardless. And so you can see that this is coming up here. If negative 40, it's going to go through this Zener here, but that's going to drop this 3 volts. So we're at 37 or whatever. Plus the voltage drop of this forward, you know, correctly biased one or whatever here. So another volt or something like that. This value here should be similar in value to your grid stopper, because this goes up to the grid stopper and then the grid, of course. And over here is the coupling cap from the previous stage. So what happens is when the circuit is engaged, we want it to have a similar resistance to the grid stopper, plus remember our grid to cathode diode. So this is our pretend diode over here. So we want it to behave similarly so that it clips symmetrically, and so this should be equal to the grid stopper, or possibly a little larger than the grid stopper. And it can be adjusted to make the clipping symmetrical. And so you can see that over here we're going to have negative 20, obviously. Over here we've got negative 37, and so this is off. You know, there's no voltage. This is blocking the negative voltage from going from this side over to this side right here. And that works like just fine. This whole thing just stays off because in order for the transistor to be turned on, there needs to be current from the emitter to the base, or the base to the emitter. In this situation, if you think you have electron flow. And so electrons are going to flow to where it's more positive. And so right now we have more negative over here, and so electrons are trying to go this way. They're being stopped here, so they can't, and so there is no current at the emitter base junction at this time. So what happens is when the swing goes positive over here, it's clipped. If it goes to 0 volts, it's clipped here. Electrons flow in. And then when it comes back down, or down, it's clipped on the bottom, because if this area right here swings down to twice the negative voltage, so if it swings down to negative 40, so it's negative 40 here, if suddenly this becomes negative 40 or negative 41 or whatever, then you're going to have electron flow from the emitter to the base, like this. And some of that flow is going to go through this 30K resistor right here, but not very much, a small amount. The majority of electrons are going to flow out this way. And so we got electrons going in when it clips at 0 volts. We've got electrons coming out when it clips at negative 40. And so you can see now, it doesn't matter where we place our negative voltage over here, it's always going to clip at 0 and twice the negative voltage. And that's how the circuit works. And that's all there really is to it. Obviously you need a NPN that has voltage greater than the total negative voltage that will be across it. So let's say, I don't know, 100 volts or whatever in this case. It could be down at 40, but you want to play it safe or whatever. And you pick these accordingly to your transistor over here, and this accordingly, and you adjust this so that you're clipping symmetrically. So if you find that your waveform is coming up like this and then kind of rounding off a little bit, but then it comes down here and then just like that, if you increase the value of this resistor right here, you can change it to kind of be a little bit more symmetric. And that's what that value is for. And that's it. So this is bug bias, you guys. I have a PCB that I'm using, but I want you guys to have a look at this, tell me what you think. And so we've tested this, we've put it in amps Sean has done a SPICE simulation of this circuit. Like I said, I've built it on the breadboard, and this completely removes crossover distortion caused by blocking. It doesn't matter what bias voltage you choose, as long as you adjust it on this side, not on this side obviously, adjust it over here for the desired output right here. If you do this properly, it completely eliminates crossover distortion, and if you put your multimeter right here, if you measure it, and you clip the amp, this will not move. This voltage, the average voltage, will stay the same. The output tubes will not turn off. They will stay on, and all is well. And the cool thing about this circuit is it drops right in. I mean, you could take a bias board like this and put it into any capacitively coupled AB1 fixed bias stage, and if it suffered from blocking distortion that causes crossover distortion, this would eliminate it. Now, why do you want to do that, I guess, is a good question. The main reason is there's a time constant associated with the turning off of your output tubes. And when you clip, let's say on a kick drum or something like that, or a big bass note, your output tubes take a while to recover and return to their proper bias point. So that's not good if you ever clip your amp. Now, if you're saying, well, just don't ever clip your amp. Well, yeah, I mean, that's great. Have really efficient speakers and listen close or whatever, and have an amplifier that's really powerful. But if you've got a tube amp that's 10 watts per channel, and you've got medium efficiency speakers in a medium-sized room, and you're listening to orchestral music, you know, you're going to clip the amp occasionally, and its recovery characteristic when it clips is going to determine how those clip transients sound to you when you're listening to music. And that's why this thing is cool. So anyway, that's it. Bug bias. I hope you like it. Thanks for watching all the way to the end of that video. I know it was long. I hope you enjoyed it and got something out of it. Now, as I mentioned at the beginning of the video, I want to share the scope with you of bug bias working. And so this first video I'm going to show you is bug bias not enabled. So this is just how a capacitively coupled AB1 fixed bias output stage would look normally. The yellow trace is the grid of the output tube, and the blue trace is the output of the amplifier. And so you can see that the top of the grid gets clipped, just like I explained in the video, and the output tubes then turn off and crossover distortion appears. So now the second video I'm going to show you is bug bias enabled, and you can see now that the yellow trace, which is the grid, clips symmetrically on top and bottom, and now the output, the blue trace, is completely free of crossover distortion. And so you can see that that's working. The third thing I'm going to show you is an image from Sean's SPICE sim, and you can see clearly which one has bug bias enabled and which one does not. So like I said, a more in-depth article is forthcoming on bugamps.com, and Sean's going to be putting that together. Thanks for watching this video.